All right, good morning, everyone. Thanks for tuning in. Today, we're very excited to have an old friend, Shahar Hadar, speaking. He's going to tell us about resolving the black hole photon ring. Please take it away.
Okay, thanks a lot for the invitation. It's a pleasure to be back here again virtually and speak about this subject, which I learned while at Harvard. So yeah, resolving the photon ring. So recently, a few years ago already, we saw the first image of M87, black hole in a distant galaxy. And this was the first image. And we think that within this image is embedded a very fine feature called the photon ring, which we can't see yet because it's blurred into the rest of the image. We don't have enough resolution to see it yet, but we believe it should be there, at least if the source is optically thin. And this feature really encodes the universal part of the image which is dictated by the Kerr geometry appearing down here by this one-line equation. So it's this photon ring feature is a very simple feature, which is predicted by just by the Kerr geometry, we think, but it's kind of it's blurred into the rest of the signal that we get, which is very noisy because of the complex astrophysical phenomena happening near this black hole. So how do we compute an image of a black hole? So this image, as I was alluding to, depends on both the astrophysics happening nearby the black hole and the general relativity, which acts as the lens, bending these light rays which emanate from the source until they get to the telescope. And the general relativity part of the image is simple. It just depends on understanding null geodesics in the Kerr spacetime. And the astrophysics part is very complicated and really, I mean, there are some things there that still demand a better theoretical understanding, even in principle, like how does the accretion disk work, and solving for a magnetized plasma in a curved background. And this is done only with heavy numerical GRMHD simulations in the best case. So kind of here, since we are interested in the GR part, kind of the main question is really going to be, how do we separate the simple GR from the complex astrophysics? Okay, and just to say, how do we compute an image of a black hole? So we basically choose a point here on the image, which is like choosing impact parameters or energy rescaled angular momenta for this light ray. And then we shoot back the geodesics toward the black hole geometry, and we see what it's doing and how much photons it picks up as it's orbiting the black hole. And then we know how bright this spot on the image appears. Okay, and basically that mathematically it amounts to solving this radiative transfer equation, which we need to integrate with respect to the sigma, the affine parameter along the null ray, the emissivity that is intersected by this light ray, and also we can take into account the absorption, which today we will not take into account. We'll put this alpha here to 0 and just integrate the total emissivity that the null ray intersects as it going around the black hole. Okay, so as I was saying, the challenge is how to disentangle this complex astrophysics from the simple general relativity in order to boost our observations, right? I mean, we want basically at least the line of observation that I'm will be interested in today is the line of observation interested in the black hole itself, understanding what its mass is, what its spin is, and what is the geometry. Basically, even if we know the mass and spin and inclination, we can start seeing if the predictions of GR giving these parameters are as we see are satisfied. So we can try to test general relativity. Okay, and of course, in an independent way to that already being done by other experiments, notably the amazing gravitational wave experiments, which are which are already probing the black hole geometries, also in a dynamical settings in a different way. So this is an independent avenue to do this as well. And it's most relevant for actually measuring the static or the stationary black hole geometry, not in a very dynamical setting like in the gravitational wave measurements, but a very stationary black hole geometry, and just to see whether the Kerr geometry is really obeyed by the spacetime. Okay, and the point, kind of one of the main points here is the photon ring is possibly well, maybe it's not the only universal part, but it's a very universal part of the image, which is determined just by the geometry. And it's basically the relations between different images. As we will see, there will be many images of every source in principle. And the relation between them is the universal information that is encoded by this lens, the black hole. Okay, and please feel free to stop me at any time. Okay, so oh, actually, maybe I should move this here. Okay, good. So very quick review of light propagation in the Kerr geometry. So this is an integrable problem, since we have 4 conserved quantities in 4 dimensions, and we can and the problem reduces to a system of first order differential equations, and they're exactly and you can write down the solution analytically, even if it's quite complicated. It's actually a quite complicated integrable system, but it's still an integrable system. And you can write down the solution in terms of these conserved quantities. So the energy, the angular momentum around the z-axis, okay, the spin axis, this is here, we choose it to be the z-axis, and this Carter constant, which is the most non-trivial of the lot. It's this is how you can write it down in terms of the polar angle, the polar momentum, and the energy, and other parameters. So this guy is quadratic in the momenta because it's they're not due to a killing, not due to a killing vector field, but a killing tensor field. This k here, so it is quadratic in the momenta. And lastly, we have the mass of the particle, which we will soon take to be 0. We'll take it to be a photon. When we take it to be a photon, actually the number of impact parameters, as I like to call them, lambda and eta, reduces to 2, okay, because only the rescaled values of the angular momenta play a role. Okay, so this rescaled azimuthal angular momentum, we call it lambda, which is scaled Carter constant, we call it eta. Okay, so these are the 2 parameters governing what light rays do, or basically, well, up to some integration constants telling us what the light ray will be like. And we can think of them, as we will soon see, as coordinates on the screen of a faraway observer. Okay, soon I will write down exactly the relation. But just the dimensionality, you can see that it works. We have two dimensions on the screen. These are correspond to these 2 parameters, lambda and eta.
Shahar?
Okay. Yes.
What equation are you solving exactly? Can you just?
It's basically the geodesic equation.
Okay.
Okay, the geodesic equation. But yeah, but when you introduce these when you introduce these conserved quantities, then it reduces to a system of first degree equations, and the radial of these, the one governing the motion in R, becomes like an energy conservation equation. Okay, you have some part here which is proportional. There's some coefficient here, but you have dr by d sigma. The sigma is the affine parameter along the null ray, and this looks like a kinetic energy in the R direction in one dimension. Okay, and you have this. This looks like a potential on the other side. Okay, with And this looks like a potential with zero energy, okay? And this potential, I drew it here in the exactly critical case, but it can be actually higher than the axis, can be the maximum can be lower than the axis. And for a certain critical value, actually for a one parameter family of values of these lambda and eta, the maximum of the potential exactly reaches this x-axis here. And then a particle with this effective zero energy can sit on the top of this potential and not move, but it's unstable. Okay, if you perturb it a little bit to the right or left, it will start either going to lower R, which is like falling into the black hole, or going to higher R, which is like going flying off to infinity. Okay, but if you balance it like infinitely precisely on the top of the potential, it can stay there. And that corresponds to a photon which is orbiting the black hole at a certain radius and not changing its Boyer-Lindquist radius, and just sitting there. And that's basically what we call the photon shell. It's this family of photons that sit on unstable so they're called spherical orbits around the black hole, and soon we'll have an illustration of them. They, in general, they're not circular because they go out of the equatorial plane. Okay, they can be like also oscillate in the polar direction, and also they advance in the time direction, in the azimuthal direction, but the radial position is fixed. Okay, and the condition that gives us this critical photon orbits is that this right-hand side of this equation and its first derivative with respect to r will be 0, and this gives a condition on these critical azimuthal impact parameter lambda and this polar impact parameter eta. Okay, so you can see that there's as a function of r tilde, which turns out to be the Boyer-Lindquist radius in which they orbit the black hole, you have a one parameter family of lambda and eta which satisfy this condition. Okay, and how does this look like in terms of the screen of the observer? So this one parameter family of conditions draws a closed curve on the screen of the observer, as you can see here. The shape of this curve depends on the inclination of the observer, on the spin of the black hole. Okay, so usually it's very close to a circle, like you can see in this blue line here. And this is, by the way, observed from very close to the equatorial plane, where you can see the deformations of this critical curve in the strongest way. And this red line, this red critical curve is the one for very high spin. So we have 490. So that's, well, maybe usually people think of this as too high to be realistic. It's really not clear, but anyway, it's interesting. Even from the geometrical point of view, that we get this very funny shape at very high spin, in which a certain part of this critical curve actually becomes a straight line in the extremal limit, in the very high spin limit, and the rest is still kind of circle-like, even though it's deformed circle.
Question?
Yes.
Can you explain what are these eta lambda parameters? Is this really something that parameterizes what people see, or how should one, or it's just some abstract parameters?
No, right. So we can. So one way to think of them is these rescaled angular momenta. Okay, but they turned out to be, from the point of view of a faraway observer, through these equations here, related to the coordinates here, to the Cartesian coordinates here, called the Bardeen coordinates, on the screen of a faraway observer. So you can see that this alpha is the x coordinate actually, and this beta is the y coordinate on this graph. But I drew here lambda and eta just in order to say that kind of morally, this lambda is the x-axis and this eta is the y-axis. But
is this really, if you took the picture, would this really be the parameters on your Euclidean parameters on your on the film or something like that?
Yes, but through this relation. So you see, it's not exactly lambda and eta. They're related to this alpha and beta are exactly the Cartesian coordinates that you would get on a faraway
I see.
screen.
Okay.
And they're related to the lambda and eta through some relation, which is not that complicated. This relation also depends, as you can see, on the observation angle, theta O, as you can see here, and on the spin of the black hole, A.
So
The
there is a
A-
way of really recalculating this in terms of what the person will see. But you're going
Yes.
to show us things in terms of lambda and eta, which are not exactly what the person will see. Is this correct?
Yeah, I usually work with lambda and eta, yeah, but
Okay.
you can transform everything in terms of alpha and beta. If you, yeah,
Thank you.
no problem. Okay, so so that's the critical curve, and okay, and there's this really funny fact about this this special family of photon orbits that you can appreciate by looking at this figure on the left. So there's a mapping between. So we were talking in the previous slide. We were talking about these orbits in the bulk geometry. So we were talking about these orbits that stay in a fixed radius and they're unstable. And on the other side, we're now talking about what happens on the screen. So actually, it's a kind of delicate point, but there is both orbits that stay in the same radius and orbits that can come from infinity and asymptote to this radius, or the other way around, or end up at infinity, where in the past, when in the far past they asymptoted to a photon shell trajectory, and they have the same impact parameters. Okay, and that happens actually because it's this marginal case. Okay, but but I think intuitively it's clear that we can have an orbit that comes from infinity and just asymptotes to a photon shell radius in the far future, or the other way around by time reversal. But the point here is that I want to say that it's really kind of confusing to understand initially, is that different radii here in the photon shell actually correspond to different angles along this critical curve. And it turns out to be angles around the photon ring in the end. Okay, so it's right. It's very different from any other celestial body that we will look at, like a star or a planet, where we look at different angles and we see different angles here. No, we look at different angles here and we see different radii here. That's really yeah, kind of contrived, and it's because of this strong lensing effect. Okay. So, and we will be interested also in near critical orbits, because of course this is a measure zero set in the phase space of all geodesics. We will be interested in near critical geodesics that wrap around the black hole a certain number of times, and we'll call that number of times n. We call n the number of half orbits that the geodesic undergoes as it orbits the black hole. And these half orbits correspond to oscillations in the polar angle. Okay, because we have both advancement in the azimuthal angle and oscillations in the polar angle, and they're not synchronized like they are in spherical symmetry when we have a curved black hole. So we have a different frequencies for these motions. So near critical, now geodesics are governed by this Lyapunov exponent, which is related to the second derivative of this potential that we saw in the previous slide. Okay, this tells us basically how unstable these geodesics are. Okay, if the second derivative is very large, then they will be very unstable, and vice versa. Okay, very large in absolute value. And this controls also, so in the case where we have some emission near the black hole and it's optically thin, we have an angle-dependent divergence on the screen, and this divergence is controlled by this Lyapunov exponent here. And so this equation tells us that the intensity along the photon ring is proportional to n, the number of half orbits the geodesic undergoes around the black hole. And that's controlled by this lambda, and it's logarithmic in the separation from the critical curve. Delta rho here is the separation from the critical curve. So turning this around, we know that we can see that in order to undergo a number n of half orbits around the black hole, we need to be exponentially close, where this exponent is controlled by the Lyapunov exponent from the critical curve. All right, so that's the intro about photon shell, photon ring. Wait a minute, what's happening here? My power is almost okay. Good. So, and we have this nice, for those who saw it already 100 times. This is the movie.
Apologies, a question.
Yes.
I don't. Maybe I shouldn't stop your nice movie, but I
No,
can
no,
run
no.
it again,
Please.
probably, right? So, can you explain again how is this photon shell defined? I mean, I understand the photon ring is this set covered by orbits which remain in a compact set, right? Is this how you define your photon ring?
Okay, so the way we call it is we call the photon ring the feature on the screen of the observer.
Okay.
We call it basically the photon ring. We basically call the collection of all the strongly lensed images. So the n equals 1 and more images of any emission we call the photon ring. Okay, and that depends on what is the source that you're really putting there. The thing that does not depend on the source is this critical curve, which is always in the same place, and that's purely a lensing thing. We sometimes also use these terms a bit loosely, okay? But basically, the photon ring is a feature on the screen. The photon shell is so we define it as the region in space-time in which you get these marginally these unstable
compact orbits.
Spherical orbits, yes, these compact orbits.
Okay, so that's the shell,
but it's
and
actually,
the ring is.
Yeah.
Because these ones you're by definition you never see, right? That's what you said. You actually can asymptote to them. So only. So somehow.
Right.
So I still don't get this ring definition because of that's the ones that asymptote to the shell.
Well, actually, the ones that contribute to the ring are the near critical ones. So these are the ones that I talked about in the bottom here. As I said, I mean, the exactly critical ones are a measure zero set. So you won't expect them to have any really intensity on the screen, precisely speaking. But the ones that are close to them, that have impact parameters close to them, that have basically that you can parameterize this by how close they are to the critical curve. Okay. So the ones that are close enough to the critical curve already contribute.
So you choose a threshold and you say, well, if it's within this threshold, then it's on the ring. That's the thing.
You can say that, yeah.
This threshold is fairly arbitrary. But it's what it's the resolution of your machine or something like that.
Well, I mean, no, you can. No, it is a precise thing. I mean, you can take a photon that arrives at the telescope and you can ask how many half orbits has it done around the black hole, and that has a precise answer. And if it's one or more, then it's part of the photon ring, basically. And there's also a region on the screen. You can think about the screen. I don't have this figure here, but you can have you can divide your screen into subrings, which are defined just by the lensing, and in the kind of, well, okay. So I'll try to draw it here. Let's say we have this critical curve here. So we can call this subring n equals 1. And then we can draw a subring which is exponentially closer to the curve and call that n equals 2. Okay, and inside such a subring, only inside such a subring, you can get a photon that underwent 2 half orbits around the black hole. So it's, I mean, there's a precise way to, that's what I'm saying, to define all this.
Okay, thanks.
Okay, yeah, I mean, but sometimes I use the terms a bit loosely, in particular, exchanging like photon shell, photon ring, maybe I do that sometimes, but it's, but one is the feature on the screen, one is the feature in the geometry, basically. All right, so this is the movie, and it's so you can see that the total image is composed of the direct photons that are kind of happen as a result of geodesics that are only weakly lensed or not very strongly lensed. And as they traverse the vicinity of the black hole, they pick up photons and they arrive on the screen. And then we have the n=1 photon that arrive exponentially closer to the critical curve and create a sharp feature on the screen. And then we have photons that undergo 2 half orbits and generate even a finer feature on the screen. So the pileup of all these subrings is the totality of the photon ring, basically. That's how we call it. The ones that are n=1 or higher. And all this together makes up the full image. Okay, this is a simulated image, which is resulting from ray tracing into a GRM HD simulation. So it's kind of the best guess to what we can expect to see. All right, so in a paper by Johnson, Lubsaska et al., and together with Dan, here we looked at these universal signatures in time averaged images. And we saw that these time averaged images in the high end limit, which actually practically starts from maybe n=1 or 2, there's a symmetry there between the subrings, in which the n=2 subring, the n+1 subring is, the image of that, the time averaged image of that is identical to the image of the nth subring, only demagnified by a factor of e to the gamma. So basically, this n subring has some profile. Let's say the n=1 has some profile, and then on top of that we get an n=2, which has the same profile, only demagnified by a factor e to the gamma, and then n=3, etc. So you can see that they're exponentially squished to the critical curve, and therefore the flux in each subsequent image is low, is exponentially smaller. So it is challenging to detect. But on the other side, these features become actually sharper and sharper. And that's why when you go to very long baselines with VLBI, very large baseline interferometry, you can hope to do that. But as we will see, you can probably hope to do that only from space. Although maybe you'll see some signature already from Earth, but it's to really finely probe it, probably need to go to space.
Question?
Although, yes.
So how big is this number E gamma or small? I mean, is this
right? Yeah. So it's
dramatically?
For Schwarzschild, for example, it's pi. So it's e to the pi. So it's about 1/20. Okay, so it's not so small. But sometimes, well, now this gamma varies as a function of spin and as a function of r tilde as you go around the ring. And when you go to high spin and certain values of r tilde, which basically correspond to radii which are in the near horizon geometry, their gamma becomes smaller. So there you can expect a demagnification which is not as large, but otherwise it's always of the same order of magnitude, roughly. I mean, it can vary by a O((1) factor, but it's yeah, in Schwarzschild it's about 1/20 or 20. It depends on what you look at. Yeah, so it's a big hit to take. All right. Good, and so I was talking about the demagnification pattern. Also, another interesting observational target, which was discussed by Gralla, Lubsaska, and Maroni, was the photon ring shape. So this shape is also a probe of mass, spin. Actually, mass is. I mean, everything is scales with the mass, but it can be a nice probe of spin. Of course, in certain inclinations, it spins more than others, but it's also you can get sensitivity to these parameters from the shape. All right. So can we resolve the photon ring from Earth in time averaged images? So this is the kind of in light of the development of the next generation event horizon telescope, which is already kind of underway, or not underway taking data, but underway being constructed. So there will be a significant improvement of the number of stations and the observation time, and a little bit also in the resolution, but not so much, maybe a factor of 2, because basically the resolution, I guess many of us heard that the Event Horizon Telescope is like making an Earth-sized virtual telescope. So, and this Earth-sized virtual telescope is limited by the diffraction limit, and the diffraction limit depends on frequency, observation frequency, and on the aperture size. So the aperture size here is the whole Earth, and that can't be easily improved if you're staying in Earth. And also the frequency can't be improved significantly because you can't go too much up in frequency because of the atmosphere. So there's absorption there. And the NGHT will go up from 230 gigahertz to 345. So it's a factor of 1.5 in frequency. And then some more stations. Okay, so maybe you'll improve the resolution by a factor of 2. But it's not like orders of magnitude improvement in the resolution. It's going to be hard to resolve the width of the photon ring. The diameter, of course, is already resolved, right? Because we see the dark spot in the middle of the image. So recently, these 3 groups here studied the question of whether with using some Bayesian analysis methods or super resolution methods, we can still hope to resolve with the NGHT or even with current EHT data, the photon ring. And there's a little bit of a debate about that, but it seems that at the moment, it seems problematic, at least with the current results. Maybe some improvement of them in the future will be possible, but with the current results, it seems like we get a photon ring which has about 50% of the flux in it from analyzing the current data, and that's problematic because that's GR allows only about 10%, maybe 20% of the flux to be in the photon ring, but not more than that, exactly because of this e to the minus gamma effect. So it's hard to get. It's impossible with GR to get so much flux in the photon ring, and so I don't think there's an agreement in the community about this issue, but it seems like the race is still open to detect the photon ring for the first time. Okay, so NGHT I already said something about. And therefore, okay, so at least a significant part of the community is now, for the time averaged images, is focusing on developing really the future space VLBI experiments in order to resolve the photon ring in time averaged images. And there are 2 proposals being discussed. One is Saltus, one is Event Horizon Explorer. And these are future experiments and of the order of 10 years, probably. And they will be, of course, transformative, because if we will have something like that in space, then we can both transcend the frequency barrier, and we can also transcend the baseline barrier. So we can, that will be a game changer for sure. But there are many technical issues there, of course, and it's really hard to do, but this is a great direction, in my opinion, to go to, especially for the photon ring, but not only for the photon ring. All right, okay, so these will be transformative, right? Because of both of these limits will be transcended, so we can really hope for much better resolution, orders of magnitude better. But what I want to discuss about today is a complementary proposal to somehow try to use existing or data which is within reach in order to detect the photon ring using the source variability. Okay, so the idea is that putting a black hole in the middle of a stochastic emission will always induce correlation in the measurements of these of the emission from far away. Why? Because well, at least, actually, okay, so we will focus on the, on light rays here, but it's even more general than light rays. If you put, if you study some field with some stochastic source, it will also introduce correlations in this field from measured from far away. But let's focus on the WKB approximation on our light rays. Okay, so if we get a flare in the vicinity of the black hole, it's connected to the faraway screen by multiple light rays. And therefore, we will have correlated events appearing close to the photon ring, at least the ones that are strongly lensed, appearing close to the photon ring, and they will be correlated. Okay, so if we have this stochastic source here, which flares all the time in different places, different times, all this emission here will look very noisy, but it actually will have correlations within it. All right, and we define this observable, which captures this effect, which is a correlation function on the screen of the intensity fluctuation. Okay, so delta I are the intensity fluctuations. Rho and phi, and this var phi, are polar coordinates on the screen of an observer, and t is a time. So we can study these correlation functions, which we call them 3D because we have t, rho, and phi. All right, but we can also coarse grain by, for example, integrating over the radial direction perpendicular to the ring, kind of summing up all the contributions on the ring, and this gives us a correlation function which depends only on the time difference and the two different angles around the ring. All right, and we can also coarse grain even more to get just the light curve correlation function, which is a standard practice. All right, so just to kind of give a graphic image of this proposal. So this is the simulation of non-rotating black hole, actually viewed from 60 degrees. What we propose is to look at the correlation function at two different positions around the photon ring. Okay, you notice that here it's the same correlation, only blurred to an NGHD resolution. And maybe the main part about this observable is that we think it's still possible to see it's observable, even if you do not resolve the width of the ring. Even if it's blurred like this, if you just record the source for a long enough time and do this averaging here, denoted by these brackets here, for a long enough time, then, and of course, the question is how long you need to do it. And that's the million-dollar question. But in principle, you don't need to resolve the width of the ring. You only need to record intensity fluctuations around different angular positions at different times. All right, so this is this in principle could work even when you're not resolving the ring, but you can measure its imprint on this correlation function, as I will describe now. And okay, so I need to speed up a bit. Actually, we need to understand a little bit more things about near critical photon orbits. So as I said, their instability rate is governed by the Lyapunov exponent, but there are two additional critical parameters, tau and delta, which are the temporal period as they go around the black hole and the azimuthal period as they go around the black hole. And these also govern these critical orbits. So together, this triplet of critical parameters basically determines the behavior of the near critical null geodesics. And how does it determine? It's easiest to see it when we look at a rotating black hole, which is somewhere here behind its own critical curve, this white dashed line. So imagine there's some black hole here. It's black, so we can't see it, but we're sitting on the spin axis. We're sitting from above and viewing it from above. And then we see some flare happening here, which we call the n=0 image. And then we will see another flare due to a light ray that went behind the black hole and came to us from here. And then a light ray that went one full time around the black hole and came from here, and then n=3 from here. And then in the n goes to infinity limit, which, as I said, starts already from pretty low n, these subsequent images will be related by a shift in delta along the azimuthal direction, by a shift in tau along the temporal direction, which is time, And they will be, and subsequent images will appear exponentially closer to the critical curve by a factor e to the minus gamma. This is how these critical parameters affect the subsequent images, right? And this can be used to do an analytical calculation of this photon ring autocorrelation function. And we did this analytically by introducing a source model, which basically is a stochastic source with some 2-point function of these source fluctuations, delta J, which are, the only thing we assumed about them is that they're local. So they're enhanced when your 2 points are closer to each other, and then they decay and they grow farther from each other. Here we chose a Gaussian profile, but it doesn't really matter. And we chose the source to be equatorial. All right. So, and we also checked in a GRMHD simulation that we get reasonable values for this, but I actually don't have too much time to discuss this. But we verified that our source is not crazy for a realistic simulation. And then we compute this correlation function by looking at the contribution to the intensity on the screen by all the different crossings of this stochastic disk. And we can, and using this assumption of the 2-point function of the source fluctuations, we can actually do the sum over all the light rays, and this integral, this radial integral along the direction perpendicular to the photon ring. And in the end, this all boils down to a collection of peaks on the autocorrelation plane, which is spanned by the time difference between the 2 points and the angular difference between the 2 points. Okay, so it's a collection of peaks with different magnitudes governed by the Lyapunov exponent gamma. Their locations are governed by tau and delta. And graphically, I can show it to you like this. So this is this autocorrelation plane. Here's the angle difference between the points, goes from minus 180 degrees to plus 180 degrees. And this is the time delay. Here we plotted it from minus 60 to 60 m, all right, in relativistic units, of course, where g equals c equals 1. And we see a universal pattern. These peaks are displaced by this critical parameter delta in the azimuthal direction, but the critical parameter tau in the time direction, the time difference direction. And they have their magnitude are related to each other by multiplying by e to the minus gamma. This is how these 3 critical parameters come in, and they govern the structure. Of course, for different sources, we will get different shapes for these peaks, but their relative positions will be related by these critical parameters. It's exactly the same as if we look at a black hole. So the picture we see does depend on the astrophysics, but the relation between the first and second and the second and third, and etc., that's only determined by GR. Okay, so this is the way kind of to separate the GR from the astro. And we studied some observational prospects, which I also won't be able to discuss now because I want to go to the last. Well, actually, I do want to state just one thing, that, well, looking at this correlation function is not exactly resolving the photon ring in a time averaged image, but I regard it at least as resolving the photon ring if you can really see a clearly separated peak in this autocorrelation plane, which is statistically significant. That will be a measure of photons that made a whole U-turn around the black hole and came to the delta. All right. And the second actually point that I want to emphasize is that there is no need to resolve the width of the ring. I said this already, but I want to say this again. Only the diameter and the temporal resolution. The temporal resolution for a supermassive black hole is really not a problem. Actually, well, sometimes it causes a problem in the other way, that you need to record for a very, very long time, but it's not a problem to resolve the timescales of a supermassive black hole, which are like, could be hours to days, maybe minutes for a smaller supermassive black hole. But that's not a problem to have enough temporal resolution. But it is a problem to record for a long enough time. All right, so let me tell you about the latest advancement here. So we measure. Okay, so So the idea is this: we measure more information on the arriving photons, not only the location on the screen where they arrive, but also their frequency. Okay, so there's a natural question: how can we harness this extra information about the photons? Can we use it in any useful way? And these pictures just are here to show you that there's a relation between the point where these photons arrive on the screen and the redshift or blue shift which they arrive at. So imagine a collection of, so we have a clear example, imagine a collection of circular orbiters around the black hole, which orbit in a circular orbit, in an equatorial orbit, all right? And they emit monochromatically with some frequency. So, and let's say this frequency is 1 here in this scale. So they will arrive at different points on the screen with different frequencies determined only by GR. Okay, this is a calculation you can do in GR. This U mu is the 4-vector velocity 4-vector corresponding to the observer, or here's to the emitter, here's to the observer. Sorry, the other way around. And P is the velocity of the photon. Okay, so there's a clear calculation in GR that you can do, and you can do it actually analytically. Oops, I sent you a thumbs up for some reason. Okay, I'm really excited. All right. So there's this map between frequency of emission and frequency of observation, which is determined only by the location on the screen. Okay, so this will be the main point, and it gives us kind of a way to translate position on the screen and frequency of arrival. All right. Now, okay, this kind of program of black hole spectrometry is not a new thing. It's well studied and successful in estimating the black hole spins of several supermassive black holes. And the main feature that you can see in the time average spectrum is that if you have an emission line here, many times, well, for concreteness, let's talk about a certain emission line in iron, which happens at 6.4 keV. It corresponds to some nuclear transition of iron or iron. Okay, so but for our purposes, what we have is some emitter just emitting monochromatically at that frequency. Of course, this is masked by emission at all other frequencies in the realistic case, but you can still see a peak above these other emissions. You can see a strong peak in this 6.4 keV for some sources. And you can try to see how this peak is broadened due to relativistic effects, which constitute both of Doppler beaming and of gravitational redshift. Okay, and this was extensively studied. These are only a few references here, and specifically, there's an interesting Nature paper by Wilkins et al. That appeared 3 years ago or so, studying certain flaring sources and their reflection that was interpreted there as a reflection from the disk of these flares. So variability was also considered, but not exactly what we're doing, but it's very related. So here is another picture of the story, and this is how it's thought of usually in the X-ray reflection community. So there's some source here. Well, I mean, actually, so many kind of the view, the current view is that there's this corona above the accretion disk, located in the above the black hole, and it's emitting and reflecting from the disk from different locations on the disk, and the different places where it reflects on the disk arrive to the observer with different colors or different redshift. So you can so that kind of causes this broadening of the iron line due to gravitational redshift and Doppler beaming, their combination. All right, and about 20 black hole spins were estimated using these. Okay, so what are we proposing here? We're proposing look for kind of the cousin of these photon ring autocorrelations, but look for them in adding this component of the frequency dependent. It's another piece of information that we can use. So basically, you can look at this formula that I showed you before for circular geodesic equatorial circular orbiters, these geckos, okay? And you can transform it into a formula that relates the angle on the screen, varify, with the redshift or the frequency that you're measuring, just by taking these R's to be the photon ring radii, and also taking this lambda to be the critical photon radius. Okay, this is basically what you're doing. And reaching this, of course, this is an approximation, which is good only in the photon ring regime. Okay, but this is the approximation. So this allows you to relate frequency and angle on the screen, and it can relate them even if you're not resolving. Okay, so here actually you can see when you are resolving, so different places in the photon ring arrive with different frequencies, but also when you're not resolved like this and you see an unresolved source, you still see the photons arriving with different colors. So they still carry in the information about where they originated in that sense. And this motivates to define these spectro-temporal autocorrelation functions, which basically are similar to the ones that I showed you before, but also have this information about the frequencies, nu and nu prime, of the two different photons measured. Okay, and the nice thing about it, okay, so you can integrate over the rho and get something which is along the photon ring and with the frequency dependence. But the nice thing, especially about them, is that you can also integrate over these two angles. Well, actually, different versions here can be relevant for different observations. For example, for VLBI, this one could still be relevant because you have information from several different frequencies. So you can still do photon ring autocorrelations, only you have different frequencies of observation. So we have kind of a stack here of information in different frequencies that you can do on the one hand. And on the other hand, you can integrate also over these angles here and get a correlation function which has no image dependence. So it's good for unresolved sources, okay? But it depends only on the two frequencies and the time delay. So this is what we call this spectro-temporal autocorrelation. And they're basically the 2-point correlations of the specific flux at two different frequencies, 2 different times. All right. So this is the idea. And we also gave a model here, an analytical model, which is now just to emphasize, I mean, this doesn't have to work only for monochromatic emitters, but to emphasize the effects of this type of observable, we took a monochromatic emitter in the rest frame and also assumed some correlation function where we also improved some aspects here and took it to be local in the co-moving frame of the emission disk or the accretion disk, which is not a very important point. Okay, so we have an analytical model similar to the one I showed you earlier, but now it is monochromatic in the rest frame. That's the main point. And different points are red shifted and blue shifted depending on the lambda and eta of each photon. Okay, and then and this work is in collaboration with Doron Shlush and Trihari Harikesh, which is on the call, and they're my colleagues from the University of Haifa, and this is again this correlation function here that you can see, and we plotted it here for various this analytical results that I'm not showing here because they're, I mean, it would be long to just explain the analytical results, but you can plot them and see that there's some non-trivial structure there. And these are the correlation peaks that you see in this autocorrelation space, depending on nu prime, and the time difference. And you can slice it in different ways. So for example, here I slice it by fixing actually nu prime, to be basically at the center of the x-axis here. So it's G0 tilde times the line frequency times 6.4 keV. Okay, so nu prime equals here like something like 2.7. And I look at the correlation as a function of nu and the time delay. Okay, so you can see you have again correlation peaks. Well, in the 3D correlation space, it will be like correlation ridges. Okay, that depends on nu prime, and t, but it's easier to look at it when you slice it into 2D pictures. So you can see that you have peaks here, and the location of the peaks basically depends again on the spin of the black hole through the critical parameters. The time delay is again roughly like the time delay from lensing. So you can see it's about 15 M. Now, some peaks are tilted here, and that happens actually because we made a more realistic assumption that the source is local in the co-moving frame. That causes this tilt of the peaks. And some peaks, so you can make the peaks elongated in one direction or the other by assuming source correlation lengths to be one thing or another. Okay, here we varied the temporal correlation length. Here we varied this co-moving correlation length. All right, so you get all these kind of structures, but at least when the peaks, when these correlation lengths are small enough, you can see quite clearly the separation of the highest point in these ridges, which is determined by the spin and mass and spin actually. Yeah, and these are results actually for small inclination, where you get a more pronounced effect. Not zero inclination, because then you just the redshift in each point on the photon ring is identical. But this is quite small inclination, not very small, about 11 degrees for these plots. All right, so this is the idea of these spectro-temporal autocorrelations. Basically, trade these angles in the image with frequencies, right? And then you can get something which is quite similar, but of course, observationally, it can open other possibilities. And these are other plots of the spectro-temporal function. They're sliced in different ways. Here we fix nu equals nu prime. So, and you get this kind of dependence. So it's different slicing of this 3D correlation space. By the way, the scale here is logarithmic. And these are these analytical results in the photon ring approximation. Yeah, I'm not yet saying that this is exactly what you see in real life. Of course, in real life, everything will be more noisy, but this is the first approximation. And you can also fix these correlation space and fix T slices and look at the dependence on the two different frequencies. All right, this is another way to look at these results. Now, observational considerations regarding this the spectro-temporal autocorrelation function. So again, here I at least am not aware of any reason that if we see a clearly separated peak with a statistical significance, that it's not resulting from lensing. I mean, maybe there's some effect that that we're not thinking about, but basically this can only come from lensing, as far as I'm aware. Just because these sources are very stochastic, very turbulent, usually. But okay, maybe this needs more thought. And again, like the photon ring correlation, there's potential for GR tests and ways to infer parameters of the black holes. Now, there's a lot of data already, which is collected by X-ray experiments, like XMM Newton and NICER and AstroSat and others. And different instruments have different strong points and weaker points, but there's a lot of data already publicly available. And it's interesting to try and look at this data, and we're trying to do that. But one main setback, at least for the current data, seems that the photon count rate is still quite low. So this is a problem that we didn't consider when thinking about VLBI, but you're not getting a lot of photons from these sources. Okay, so if you want kind of temporal correlations and you're getting one photon per in a very long time, then it's going to be hard compute this correlation function. So actually, it turns out that more than the spectral resolution, and certainly more than the temporal resolution, the main issue, which it's not yet clear if we expect to see this with current data or not, but the main issue, which it would be great if it could be improved in future experiments, is the photon count rate, is the collecting area. And actually, Athena, the future X-ray observatory, is expected to improve on all of the different factors of these observations by at least a factor of 10. So this should so this would be very beneficial for this kind of observable. But we may get lucky. I mean, there's a lot of data we can already analyze with this new way to look at this data. So it would be interesting to do that. Now, there's a lot to do in the future. Mainly, maybe the main thing is really to look at more realistic settings. So first of all these calculations that I showed you are done in the photon ring approximation, where everything can be done analytically, and it's very nice. But really, the main contribution is of the lower ends, the lower images. For example, correlation between n equals 0 and n equals 1. So we really need to get I mean, there surely will be correlation there too, okay? Because the correlation just comes from the fact that there are multiple images of every fluctuation. But to characterize this correlation, it really demands a bit more semi-analytical studies and fully numerical studies in realistic simulations, like in ray-traced GRMHD. And there are other things that also can be done. And also thinking about other observables, more general, or just using other data. So in summary, what I tried to tell you is that the relation between the different images, and especially the photon ring part, is the universal black hole data in images and other black hole observations. And revealing this photon ring is an ongoing challenge, and it's using different instruments and methods. And there's quite a lot of excitement in this field. And with the question of how finally can we probe the black hole space-time geometry with this upcoming data. Thank you.
All right, thank you, Shahar, for a great talk. We have time for questions, so just unmute yourself and go ahead and ask.
So I guess with the frequency dependent signals, there's going to be some astrophysical effects that cause like variation in the frequencies as your photons are moving through the geometry. And I assume there's some way to like sort of correct for or like subtract these changes out.
Well, I mean, this iron line frequencies, I mean, there are many emission lines.
Mm-hmm.
In general, there are many emission lines, but where these emission lines are located, that's not I mean, that depends only on nuclear physics, on atomic physics. I mean, these are frequencies that we can know, that we can measure on Earth, these
Mm-hmm.
transitions. So they're really, yeah, that's why they're useful for us, because it's like a beacon. We know the frequency it originates with. Of course, it's a bit of an idealization, but that's the idea, that that we have a signal emitted with a very specific frequency, and these nuclei can be excited in various different ways, but the transition frequency is always the same. So and once this photon is emitted, I mean, we're assuming that, and this is also done in the standard studies of the spectra of black holes, that of AGN, that it's only relativistic effects that are affecting it. So yeah, it's
Oh, okay, yeah.
yeah.
Okay, yeah, I guess. But yeah, I was imagining something that's not. So you can really just say it's just purely relativistic effects for these types of.
Yeah,
Okay.
yeah, just because it's the same. Well, it's actually a remarkable thing, but it's, if you think about it a little bit, but it's just assuming that the iron nuclei there are the same iron nuclei here.
Mhm.
And I mean, maybe we take it for granted too easily, but it's at least that's the assumption, and that's all.
Okay, yeah.
Yeah.
All right, well, if there are no more questions, let's thank Shahar again. Thanks for the talk, Shahar. I'll
Thank
stop.
you.
Thank you.